Exam 2 is coming up in a few days, this coming Monday, and so let's do a review of everything we've covered between the two exams. So the exams are over. Chapters 9, 10, and 12 through 14. Those five chapters cover three major topics. First, some of the basics of thermodynamics, free energies, open systems, and a whole host of thermodynamic relationships. For the most part, we haven't used those, and so though they're on the exam in principle, there probably won't be very much on the exam that cover these things in and of themselves. They'll be used in the course of the exam. A lot of this stuff will be used, in fact, heavily in the course of the exam, but not so much questions about the thermodynamic formalism itself, probably anyway. I haven't actually written the exam yet, so I don't know for sure, but that's what I predict. Then the second topic is the thermodynamics of chemical reactions. Most of that centers around delta G equals delta G0 plus RT log Q and the consequences of that, things to do with the equilibrium constant, for example. And especially later on, the binding constant, dissociation constant, Kd. But there's also a little bit of fundamental stuff in this section as well. And then finally, the last section, major part of this part of the class, is all the stuff on the thermodynamics of binding, the strength of binding, the specificity of binding, and the effects of cooperativity and allostery on binding. I put here also the lectures that go with each of these subjects, so if you want to study them in terms of these three topics, you can know which lectures to look at. What we're going to do right now is just use these lectures to go over briefly a little overview, a kind of outline really of the major topics. So first of all, and to do that, I've put little pink marks throughout all these things. So there you can see them. These guys that show the parts of these topics that we'll hit on as we're going through this overview. Of course, there's lots of stuff in between, and all that stuff is also worthy, and in fact, you have to read some of that stuff to know what the highlighted stuff is even talking about in a lot of cases, but these are the highlights nonetheless. So first of all, under this main topic, so we're looking, what I'm showing here is lectures 15, 16, oops. Lectures 15 and 16. So we're talking about section 1 here, the thermodynamics. And the first one is the definition of the free energies, Gibbs free energy and Helmholtz free energy. The Gibbs free energy is H minus Ts, and we saw that under conditions of constant temperature and constant pressure, so if there's constant T, constant P baths present, and so that the processes occur under constant T, constant P conditions, then the change in the Gibbs free energy is proportional to the change in the total entropy for both system and surroundings of the universe, and that's why delta G is useful. It means that you can tell which way a process will go spontaneously by looking at the value of delta G. So if delta G is less than 0, so if G is a minimum at equilibrium, then when delta G is less than 0, you're heading towards equilibrium, and therefore the reaction will go in a spontaneous forward direction. If it's equal to 0, you're already at equilibrium, and if it's greater than 0, then you're going backwards. So a delta G that's negative, therefore, is a favorable thing for the process to go. A delta G that's greater than 0 is an unfavorable thing. We'll see that a lot in the chemical reactions down below. We also saw that the delta G for some process has an enthalpic contribution and also an entropic contribution. This delta S, remember, is the entropy change for the system alone, without any contribution from the surroundings. The contribution from the surroundings entropy comes from, well, is accounted for in this delta H term. The delta H term is not the same thing as the delta S of the surroundings, but it accounts for that. It accounts for the effects of that. We saw that what the delta H's term is accounting for is energy changes, heat changes that under constant pressure conditions that have resulted in energy, heat energy being spread out to the surroundings or being absorbed by the system from the surroundings, therefore either raising or lowering the entropy of the surroundings. And so there's two terms, right? One that's accounting for the surroundings entropy changes, one that's accounting for the system entropy changes. Yeah, we saw that even in biological systems where two proteins are coming together, or a protein and a DNA, the binding part, the delta H part, the part that accounts for sticking, and we'll see this importantly in the later parts when we're talking about binding over here, that, that those contributions to delta G amount to contributions that result from the fact that heat is either absorbed or emitted to the surroundings during the binding process. A favorable reaction can be driven by delta H changes to the surroundings, and that's delta H is often the biggest term, but not always. But it can also be driven by changes in entropy, favorable changes in entropy. So, for example, in a dissolving process like this, the delta H contribution probably isn't favorable because you have to break all these interactions, all these little weak bonds between the molecules in the crystal. But it can still be favorable, even if that's true, because of the entropy gains from releasing all those molecules into the surroundings and all their increases in translational entropy. All right, then there's the Helmholtz free energy, which is almost the same thing as delta G, right, except that it's got an energy here rather than an enthalpy. And that's because under constant temperature, constant volume conditions, so not constant pressure anymore, the change in the Helmholtz free energy is proportional to the change in the entropy of the universe. The Helmholtz free energy is also minimum at equilibrium, and therefore the rules for delta A changes are the same as for delta G. It's just that the conditions, the things that are held constant are different. So a negative delta A is favorable, a delta A equal to 0 means you're at equilibrium, and a positive delta A is unfavorable. A lot of delta A, or Helmholtz free energy, is useful in its own right, but a lot of the interest in application of Helmholtz free energy comes from this relationship down here, which gives the connection between a thermodynamic fundamental potential, something that can give all the thermodynamic properties of the system, and this statistical quantity, the partition function, the canonical partition function that we talked about last time. And so this relationship between statistical mechanics and thermodynamics is absolutely, it's hard to overemphasize how important that is. It's a really important relationship which is very widely used, and for that reason, Helmholtz free energy is used more often than you would think. Okay, that's it for, I think, oh no, quite, I take that back. Oh yeah, that was lecture 15. Lecture 16 then, going on with chapter 9, gives a lot of relationships. There's the Euler relationship. So this is the part where I basically just core dump all of the most important thermodynamic relationships. The Euler relationship that basically defines the energy, entropy, enthalpy, Gibbs free energy, and Helmholtz free energy in terms of the more usual thermodynamic quantities like volume and pressure and chemical potential and mole numbers and so on. We've used these a little bit, especially this one, but I'll just leave them here because we haven't used them a ton, and I don't there's not too much to say about them. They're useful as general relationships, but they don't give a whole lot of insight, so we won't talk about them directly here. Yes, it is important. This one is important. That's this one up here, really. The chemical potential is the same thing for a pure substance as the molar Gibbs free energy. We use that to write this relationship, right, for chemical thermodynamics, chemical free energy changes, and that's where this relationship comes in. Then there's a whole bunch of first law relationships. Also, I'll say the same things about them. They're important, but maybe less important in this class because we won't deal with the formal structure of thermodynamics as much here as we would in a class that was dedicated to thermodynamics, either at the undergraduate level or at the graduate level. These things will be big if you take a thermodynamics class at the graduate level, but less big here. Then there's a whole bunch of partial derivative relationships. We haven't used a whole ton of these, and there's even a whole set of them that I haven't even written down at all, but but we have used this one, and we've also used this one. And so from time to time they become important, and it's good to know that they exist. All right, that is that. And now at the end of chapter 16, we talked about this set of standard equations of state. That's very important. It's from a practical point of view. What are all the equations that you need equations of state in order to actually do calculations in thermodynamics? What are they all? Well, there's a set related with pressure volume variables. It's the ideal gas law, and for gases, and then this rule that the molar volume is approximately constant, the incompressibility condition for liquids and solids. These are, of course, approximate, but pretty good in most situations. There are better gas equations of state. There are better solid and liquid equations of state. But these are all do for our purposes. Then there's the ones associated with energy and temperature. Those are basically the heat capacity relationships, either for constant volume situations or constant pressure situations, and they give either the energy or the enthalpy due to a temperature change. For the monatomic ideal gas, the situation that we like to use a lot because it's relatively simple, they take these relationships, take this form and this form, and of course we've used that a lot in the previous parts of the class. We won't use them as much in what's coming up. And then finally there's the big and most important one for this part of the class, and that's the chemical potential equation of state, which says that the chemical potential is some standard state chemical potential plus RT logarithm of this quantity, the activity, which basically accounts for concentration effects, changes due to concentration effects. I say later, and I'll emphasize later, that this term is due entirely to translational entropy. Nothing else. All the other effects are accounted for in this other term. And that means, because this term ultimately gives rise to delta G, to our important, that's not there, okay, to our important relationship for delta G. You can see it looks kind of like this, right? This delta G comes from here. This log Q comes from here. Because the translational entropy is the origin of this term, it's also the origin of this term. And since this controls equilibrium for pretty much every chemical reaction, translational entropy plays a huge role in chemistry. Let's see, what else is there to say? Oh yes, the list of standard ways of writing the activity. So for gases, it's usually the ratio of the partial pressure of each gas over some standard state partial pressure, usually 1 atmosphere or 1 bar. Sometimes it's written in terms of, sometimes even for gases we use molar concentration, but that's more unusual. Depends on the standard states that apply when you get your numbers for delta G0 and delta H0 and delta S0 from tables, right? You got to make the standard states that are in the tables match the standard states that are implied by your choice of activity, your representation of the activity. For solvents and ideal solutes, the mole fraction is usually the concentration variable that's used to define activity. And the most common one by far is for dilute non-ideal solutes, and then it's usually molar concentration divided by some standard state concentration, almost always 1 molar, though occasionally it's not 1 molar. One of the issues that's come up, and we'll talk about later, no, not here, but in a later time, is the fact that you can have standard states that involve both concentration and pressure or other concentration type units, mole fraction, for example, all in the same expression, and that's fine if it's consistent. In fact, it's even necessary if it's consistent with the standard states that apply for the numbers you got from the tables. All right, that is the first part. The next part has to do with the thermodynamics of chemical reactions. Let's get that. Here it is. And so this is the second part of our 3 parts here. The thermodynamics of chemical reactions, chemical equilibrium. And that begins by talking about what are the driving forces for chemical reactions. And we saw early on that it's a chemical potential difference of some kind. In this particular case, it's for a very simple reaction with just one reactant and one product, right? So it's just a difference between the chemical potentials of A and B here. But in more complicated cases, if it were a more complicated chemical reaction, this delta U, or the difference in chemical potential, still applies, remember. So for a reaction like this, the only thing that changes is that the effective chemical potential difference becomes products minus reactants weighted by stoichiometric coefficients, right? It becomes C mu C plus D mu D minus A mu A plus B mu B. So it's still chemical potential for products minus chemical potential for reactants. It's just that the chemical potential for products now involves more than one chemical species and so on. All right, if the chemical potential difference is greater than 0, that means the free energy, the Gibbs free energy, rises when more product is created, and that means the reaction will want to go backwards. Gibbs free energy rising this is all under constant temperature, constant pressure conditions. That's the usual conditions. But let me just point that out. That means delta G, or Gibbs free energy, is actually rising. That's unfavorable, so the reaction is going to go the other way. If there's no chemical potential difference between the two sides, then you're at equilibrium, and if the chemical potential is negative, that is, if the chemical potential goes down, that means the free energy is also going down when you create products, and that means the reaction will go forwards. Yes, then we talked for a good deal of time about where this equation of state for chemical potential comes from. There's a long derivation here, and I think it's worthwhile looking at because you're likely to see something like that again in later classes, at least if you stay in a research-oriented career. But I won't go through it here. I just point out that it is here for you to peruse at your leisure. And the conclusion that it comes from, I mean, by doing this derivation, we can see very clearly that this standard state chemical potential accounts for all the molecular properties except changes during the course of reaction that are caused by changes in the number of translational microstates available to the system. So if the final system has more freedom to move around, then this term comes in. If the final system doesn't have any changes in the ability of things to move around, then only this standard state term applies. And that accounts for everything else, the changes in mass, changes in bonding, changes in rotations and vibrations, changes in the solvent, changes in temperature and pressure, and so on. All those things are accounted for by this one term that we normally don't even pay that much attention to, and only the translational effects are accounted for by the second term. All right. The reason that's important, of course, is the very next thing is deriving our sort of central equation here. This is the chemical driving force. It's really delta mu. I'm calling it delta G per mole, right? Delta G bar is per mole. But that's just a renaming of a chemical potential difference. And I rename it because that's the utterly traditional thing to do. Even out in the chemical literature where people should know better, they use it, they still call it delta G. I'm not sure what the historical reasons are for that, but I won't try to fight them. So delta G is equal to delta G0, the standard state Gibbs free energy change, plus RT log Q. This Q is going down here. The Q is this ratio of powers of activities raised to stoichiometric coefficient powers. That's familiar, I think, to everybody. The standard state delta G is the difference in delta G's between products and reactants. So it's products minus reactants weighted by stoichiometric coefficients, the usual difference, the usual thing. And therefore, this term is accounting for all the molecular effects, bonding changes, rotation changes, vibration changes, all that stuff, solvent changes. And this term is accounting only for the effects of changes in the translational microstates, the ability of things to move around. This term, of course, is utterly important and plays an enormous role in chemistry. All of the stuff having to do with equilibrium and constants and stuff comes from this term, but it's really only accounting for one of the many effects, and that just highlights how important that one translational contribution is to chemistry. All right. If you're at equilibrium, then the delta G is 0, and solving for the reaction quotient under those conditions gives this relationship. We identify the equilibrium constant with this part of it, and so this relationship holds. The equilibrium constant is e to the minus delta G0 standard state over RT. And at equilibrium, that means that the equilibrium constant is equal to all the equilibrium activities in their products over reactants ratio. It can also be shown, I emphasize, that the equilibrium constant is equal to the number of microstates. It's a very statistical thing. The number of microstates for the products at their standard state divided by the number of microstates available to the reactants at their standard state. It's really that simple. It's just how many microstates were there at the end versus how many microstates were there at the beginning. That ratio is the equilibrium constant. And so though we came to the equilibrium constant in a rather roundabout way through all this thermodynamics, the actual physical meaning of the equilibrium constant is very fundamental and very simple. It's just the ratio of microstates available before and after. Okay, what's next? Where is the next pink mark? All of these are examples. Yes, I marked this. I think that everybody's clear about this, but there's two common sets of standard states. The chemist standard state, where solutes are all at 1 molar, gases are all at 1 atmosphere, and all the solvents and solids are pure. And then there's a biochemist standard state, which is exactly the same, except that for H plus ions alone, there's an exception made for H plus. In that case, the standard state is at pH 7, which is 10 to the minus 7 molar, very different than 1 molar, of course. But that's because in biochemistry, a 1 molar H plus concentration corresponds to a pH of 0, very acidic solution. That's, of course, never encountered in biology, basically, because everything would be dead at that pH. And so it's more convenient and useful to use this 10 to the minus 7 molar pH 7 standard state. Yeah, here's an example that I highlighted with the pink dot here because it uses, and I won't go over it in detail, but I bring it up for your attention because it uses this mixed activity, mixed standard state situation. So the reaction quotient is ratio of pressures and molar concentrations both in the same expression, and there's nothing wrong with that. There were some homework problems on this topic too. Let's see. That is it, I think. No, not quite. Okay, Hess's law. I won't go over that because I think everybody's clear about that. There are some rules for combining equilibrium constants. Remember that. We'll use that. We do use that in the later sections of this part of the class. If you add two reactions, you multiply the equilibrium constants. You add the delta H's and delta U's and delta S's and delta G's. If you multiply some reaction by some factor like 2, then you raise the equilibrium constant to that same power. And it doesn't have to be a 2, it can be a pi or any other number. If you reverse the reaction, then the equilibrium constant becomes 1 over that. That's like the relationship between the affinity constant, right, and the dissociation constant, Kd, later on, right? The affinity constant is for binding, dissociation is for dissociation, and they're just 1 over each other, right? Ka is 1 over Kd, and Kd is 1 over Ka, right? Yes, let's see. Then there's the Van't Hoff stuff. It's pretty likely that'll be on the exam. That's a very standard, utterly standard Chem topic and very widely used in the literature, very widely used by everybody at every level of research. And so I will probably try to encourage everybody to study that stuff. We did a bunch of examples like this, so I won't go through the examples here, but remember that the Van't Hoff equation can be written this way, or by taking the log of both sides can be written this way. Those are both the 2-point forms of the Van't Hoff relationship. Or it gives rise to a linear relationship between log of k and 1 over t, and that gives rise to a Van't Hoff plot. The slope of a Van't Hoff plot, so log k versus 1 over t is a Van't Hoff plot. The slope of that is related to the delta H, and then you can use that information to get the delta S as well. So the reason Van't Hoff is so widely used is because it's an absolutely standard way of getting not just delta G, which you can get directly from K, right, but also delta H and delta S by watching how the equilibrium constant changes with temperature for a chemical reaction. You can get delta H and delta S for the chemical reaction. All right, we talked about the Le Chatelier principle and how that's related to the equilibrium constant, to the Van't Hoff equation, but again, I won't take the time to go over that now. Is there anything else left in this section that I think is worth highlighting? Yes, one more topic, and that is maybe not the most important topic. There it is. But I thought I would remind people again of this model, this very simple model for protein folding, not because it's important in its own right, but because it's just about the simplest example of using all the ideas that we've been developing so far to come up with a very simple model for a rather complicated process. So the process of a protein going from a random coil arrangement to a folded arrangement. Boy, that looks like something that would take just an enormous amount of detail and difficulty to understand, and yet we can understand it at some low level, at least some features of it, by this very simple model. We think about the contributions to this folding process from a thermodynamic point of view, and we say that when it's in the unfolded state, there isn't very much interaction among the amino acids. When it's in the folded state, it's much more likely that you get strong interactions among the amino acids. We say that that's favorable, that the amino acids tend to stick to each other by a whole variety of different mechanisms, and so we attribute a delta H contribution to the overall delta G of folding. I mean, the purpose of this model is to come up with a model really for the standard state delta G of folding, of going from unfolded to folded. And one of those contributions is a delta H contribution. Later we talked about all the delta H contributions, that there can be lots of them, 5 of them we talked about. Here we've rolled all those into one number, and that's why this model, part of the reason why this model is so simple. But even so, we get a useful number. We pick a particular value for how much sticking there is between the amino acids, and that gives us our delta H contribution. Then we identify two different entropic contributions, one from chain entropy. So when you fold up, you lose the freedom to move the chain around a lot. That should be unfavorable. We write a contribution for that. In terms of how many microstates we think are lost in the course of folding things up, that gives one delta S contribution. And then the hydrophobic effect, right? The water rotation contribution is actually favorable because the hydrophobic amino acids are now sequestered in the center. That means there's less surface area of interaction between the hydrophobic residues and the water. And we can also talk about how many microstates are lost per residue due to the hydrophobic effect. That's a favorable one, and that gives another contribution to delta S. Adding those things up all together gives us our final model for the delta G for folding. There's the delta H contribution here, and then there's the two delta S contributions added together, and you get this very simple expression for how the delta G should depend on temperature. And if we wanted to change the model, or if some other situation came up and some of these numbers are no longer good, since we've derived our model from simple physical ideas up here, we can do that. We can see what a change in a particular situation would do to all these values, and therefore we would get different numbers down here and maybe even a slightly different expression, but the same ideas would hold. And we did two things. We saw that the delta G is not very stable per residue. You have to have the whole thing folding up at once in order to get a big enough delta G contribution so that it will really actually stay together as a stable folded structure. The folding must be cooperative is the conclusion. And we also used that expression to predict what the melting temperature would be. At what temperature does the delta G, the standard state delta G at least, go to 0? And we saw that that gave us a number of about 55 degrees C, which is a typical value for the denaturation of most proteins, so it gave something reasonable. All right, that is it for that block of lectures. Now let's go to the next one, which I think, let's see, let's close this and go to the next block, which I think is, yes, this one, right. Oops, that's not what I wanted to do. Yeah, there it is. Okay, so now we're into the third section of the class, the final section, which has to do with the thermodynamics of binding. So this is the part, I mean, we're doing this now. The rest of this is mostly pretty general, doesn't really have a lot of biology in it, isn't specialized for biology. But this last section is the place where we chose this particular topic because it's so important to biology, and there's a lot of biological, structural biology, especially biological molecular structure, that informs this part of our section, and therefore is useful for people who are interested in biology, biophysics, biochemistry. All right, so thermodynamics of molecular binding and recognition. And after a little bit of an intro, the core idea, of course, is that we're basically just studying this one chemical reaction, the binding of two molecules together, whether those are both big molecules or whether one of them is big or whether and one's small or whether they're both small. Doesn't matter. Everything we're saying about this section applies no matter how big or small the molecule is. There is a delta G for this process. It's the delta G of binding. That's basically the thing, the contributions to which, no, I don't have them here, we talk about later, right? There's those 10 contributions, 5 of them enthalpic, 5 of them entropic. Those are all contributions to this delta G of binding. They can be used to build models, just like that model for protein folding that we just talked about. The delta G of binding is related to the affinity constant, right, which is the equilibrium constant for this reaction, by the usual relationship minus RT log Ka. But we've seen that it's the dissociation constant that's usually much more convenient to use. I mean, we could use the affinity constant all the way through, but the dissociation constant is more convenient in most cases. And for that reason, it's by far the most widely used thing. The affinity constant isn't used very often in my experience outside of, classroom exercises. It's the dissociation constant that everybody uses. And so we want to translate these relationships into the dissociation constant. Kd is equal to 1 over Ka. So if I plug that in here, you can see that delta G of binding is going to be equal to, all it's going to change is this minus sign. It's going to be plus RT log of Kd. So unlike the relationship between delta G bind and Ka, there's a plus sign here in this relationship when it's Kd that we use. Yes, and the delta G of dissociation, of course, is just the negative of the delta G of binding, and that's another way of getting this relationship. Remember that a small value of Kd, it corresponds to tight binding. A large value of Kd corresponds to weak binding. The next thing we did is look at this quantity, the fraction of protein that has a ligand bound to it, as a function of the ligand concentration, and we derived this relationship, which was used pretty heavily throughout the rest of the section. The fraction bound is 1 over 1 plus the dissociation constant Kd divided by the ligand concentration. And that could be expressed logarithmically too, though we didn't use that really after this because the book doesn't use it. Given that, we see, what this relationship shows you is that the tendency to load up our protein with a ligand and therefore get a large fraction bound is controlled by the value of Kd. The range of concentrations of ligand over which the protein will bind, it will load up, is controlled by the value of Kd. So if the ligand concentration is much less than Kd, then the fraction bound will be close to 0. If it's on the order of Kd, roughly the same as Kd, then the fraction bound will be about a half. And only when the ligand concentration gets much, much bigger than Kd will the fraction approach 1. And so we can talk about, that's just fraction bound as a function of ligand concentration. We can talk about millimolar affinity, right? When Kd is 10 to the minus 3, that means that when ligand is 10 to the minus 3, we're going to start getting things loading up. We can talk about micromolar affinity. When the Kd is 10 to the minus 6, then only when ligand concentration gets to be in the micromolar range will you start loading things up. We can talk about nanomolar affinity, we can talk about picomolar affinity, femtomolar affinity, zeptomolar affinity, going down and down and down. All right, we saw that for each of these values of Kd, there's a corresponding delta G of binding, which falls in this range, right? These are the real value, the true values, but these are the ones that are close, and for rules of thumb, these are the values you usually use. Anywhere from about minus 20, anything weaker than about a minus 20 kilojoules per mole delta G of binding gives you such a weak affinity that you probably don't see much effect. Down to about minus 90, that's the range. At that point, at minus 90, you've got such strong binding that the thing just won't even let go. Picomolar and femtomolar binding affinities are so strong that the thing just never lets go. Biotin, biotin has a Kd in this range, and once avidin binds to biotin with this range, the thing never comes off. You gotta do something. You gotta denature the protein to get it off. All right. What's the next topic? Here we are. Oh, scattered plots. If you want to find out what the Kd is, but you haven't really identified the protein, you don't even know what the protein concentration is, then with this derivation you can show that by plotting the amount of ligand that's bound, you got to have some way of knowing that, but there's lots of ways to do that, over the amount that's free versus the amount that's bound, and making a plot of that, you should get a straight line, and the slope of that is minus 1 over Kd. So very useful, widely used. And what's next? All right, that leads us to finally, all that sort of preliminary, basically descriptors, quantitative descriptors of binding. Now let's talk about the qualitative stuff. What are the molecular features that actually give rise to binding? I wrote, these are my own. These are obviously not from the book. If you've read the book, you know that. These are my own list of contributions, 5 of them contributions to delta H, 5 of them contributions to delta S. And let's go very briefly, so we went through these carefully before, but let's go through them very briefly again. First of all, there's H bonding, which is good at pattern matching, right? Good for specificity, not so good for strength of binding, because when you take the ligand out, you get H bonding to water. And so in both places, both for the ligand and for the protein. And so oftentimes H bonding doesn't contribute that much to binding, but it does contribute a lot to specificity. Here's an example of that. We looked at that. Then there's electrostatics. Same story, basically. The patterns on the two binding surfaces have to be complementary, right? Wherever there's a plus on one side, there has to be a minus on the other side. But if they are complementary, that doesn't mean that you'll get strong binding necessarily, because you've got to take the water away from those charged species in order to bring the two molecules together, and taking the water away costs you energy, and whether you get back as much energy as you paid in order to get the water away to desolvate is a question that varies from case to case. And sometimes you lose more, a lot of times you lose more energy than you gain when you, electrostatic energy that is, than you gain when you bring the two molecules together. But it does provide another type of pattern, and so it's also a contributor to specificity. Then there's all these stacking interaction kinds of interactions. There's 2 examples of that. The DNA molecule is, of course, a primo giant example of that. Stacking interactions are the primary driving force for the formation of the double helix in the first place. And also here's biotin-avidin, or streptavidin, and a variant of avidin. A lot of the binding strength is due to stacking interactions between aromatic amino acids here, tryptophan, and the hydrophobic parts of the biotin molecule. And finally, there's strain energy. We didn't talk much about that just because it hasn't really come up that much, but it comes up a little. And that's the fact that sometimes in order to get good binding, you got to bend the molecule, and that's always unfavorable. It always costs you energy to bend something. Then there's 5 entropic contributions. Some of those are obvious. The changes in translational degrees of freedom, if you go from 2 molecules to 1 complex, you obviously lose net translational degrees of freedom. Likewise, rotational degrees of freedom and configurational changes. Binding generally makes all of these unfavorable. Sometimes you release water when you bind, and that's favorable. You're releasing water to run around in solution more freely. And then there's the hydrophobic effect, which is, of course, a little bit more subtle and also very important. We spent a lot of time talking about the hydrophobic effect. I won't go over it much here. In fact, I'll skip a lot of this stuff because we've gone over it so extensively already. But it's the effect that's caused by the fact that if you've got a hydrophobic surface, then the water molecules can only hydrogen bond to other water molecules. This hydrophobic surface doesn't have any hydrogen bonding opportunities, and that constrains the rotational freedom of the water molecules that are near the hydrophobic surface. And again, that's the primary driving force for an awful lot of biology. The DNA molecule and most protein folding, all those things, the formation of lipid bilayers too, even more actually. It's the driving force for the formation of lipid bilayers. A lot of biology is due to the hydrophobic effect. This is more about the hydrophobic effect. Here's the other contributions, right? The loss of translational degrees of freedom, 6 over here, 3 over here. The loss of rotational degrees of freedom, 6 over here and 3 over here again. And then the general tendency for both amino acid side chains and polymer molecules when they bind to lose configurational freedom. all those are generally unfavorable upon binding. And I think that is it for that batch of lectures. We have 2 more batches of lectures, though, coming up. Let me close this one out. Open the next one. 33, I think, is the next one. Yeah, and now we're going to talk about specificity. We've talked about this relatively recently, so I'll go over this pretty quickly. But specificity is basically due to pattern matching. Yeah, here it is. The patterns that are most important are patterns of H bonding, patterns of electrostatic, and the shape, right? The 2 molecules have to fit each other in order to get good contact and therefore good binding. Those provide most of the specificity. The hydrophobic effect usually provides most of the driving force, the strength of binding. And so let's see, what do I want to say? I don't have any pink marks on these things. Here we go. All right, so that's all I guess I'm going to say about the strength, about the specificity. No, there's more to say. I think I skipped some stuff. I think I'm missing some stuff. Yes, this is already specificity from last time. I missed some stuff. So this was lecture 33. I missed some lectures. Yes, 26. Here we are. 31 and 32 is what I missed. All right. All right, specificity, yes. So everything I just said is right. First of all, specificity is important, of course. You don't want everything binding to everything. You want things to bind only to the things that matter. And remember, the big thing about specificity, it isn't obvious at first, but it depends on how concentrated your ligand is. If you put enough ligand in, you lose all specificity. If you put too little ligand in, you don't get any binding to the molecules that you need to load up. And only when you're sort of in the range of the ligand concentration roughly equaling the KD of the target protein do you get good specificity and reasonably good loading. There's this specificity factor alpha, which is the ratio of the ligands that are bound to the true target to the ligands that are bound to everything else. It's defined in this way in terms of concentrations, and then we derived this relationship that gives between alpha, the specificity ratio, and the concentration of the ligand in question. And we've done a number of examples showing what that looks like and how that works in relatively simple cases. Of course, in complicated cases, this calculation down here in the denominator becomes a mess, and so we won't do that. But simple cases are possible, and we've done a number of examples. Let's see, what's the next pink dot here? These things are all good examples and important and very useful for people interested in biology, but again, we've gone over them fairly recently and they're qualitative, so I won't go over them again. And that is it. Yes, that is it. All right, back to lecture 33 then, which is now talking about, there it is. And this is our last lecture, actually, so the end of this review. Talking not about specificity anymore, but about cooperativity and this is all review, and switching behavior, right? The problem is that if you want to get binding to a receptor, a switch of some kind, or a sensor of some kind, or a trigger of some kind, then you need a huge range of concentration. You need a change in the concentration that's enormous before you can get a good switch, if you only have the usual non-cooperative kind of binding. You need a 100-fold change in order to get a good turn on if it's just normal uncooperative binding. And so, suppose you have a situation where you've got multiple subunits, and therefore you can have multiple bindings. We used hemoglobin for most of our examples, where you've got 4 subunits and therefore 4 possible bindings. In that case, if you derive what the what the signal function looks like. So here's our signal function, and here's how it depends on the ligand concentration. Then you get that the response of the signal to changes in ligand concentration gets much steeper, which means it's much more sensitive. It turns on much more strongly when the ligand concentration changes. And that depends on how many things are involved. This was just 2 guys involved. But suppose you have, we'll come back to that because that's a fairly important point. Suppose you have 3 guys involved. Then it gets even more sensitive. And if you have 4 guys involved like this down here, it gets even steeper. The steeper it gets basically in this part of the curve, the more sensitive it is. Coming back here, here's our simple 2-state hemoglobin model. And it's this point that I wanted to come back to. My pen seems to have run out. Let's see if I can get a little bit of juice here quickly in order to make a few more marks, and then we're done. Here's the response when just one thing is bound for the low affinity state. Here's the response for the high affinity state. When both of them are present at once, then you get this crossover behavior, and that's what gives rise to the steep part of the curve. All right, that's not the most important point, but a useful one for understanding how these things work. And I think with that we are done. Good luck on the exam, and if you have questions, we'll have another session on Monday where questions can be asked, and also my office hours on Friday, so please come to those.